We will now look into some practical aspects of using GNSS measurements for volcano monitoring. The photograph shows a person setting up a GPS instrument near the Eyjafjallajökull volcano during its eruption in 2010. The white disk is an antenna that receives the signals from the satellites and feeds it to the receiver that is sitting in the yellow box on the ground and powered by a car battery. On the ground underneath the antenna, there's a metal pin called a benchmark that is cemented into solid bedrock to stay there for decades. This benchmark is the physical point that we are tracking position of to see, for example, if the volcano is deflating or inflating. The antenna needs to be accurately positioned above the benchmark. On the example shown, a three-legged surveyor's tripod and an optical plummet have been used to center the antenna over the benchmark. The surveyor is measuring how high the antenna is above the benchmark, and a pile of rocks is used to secure the tripod in place so that it can be left for days in the Icelandic harsh weather. Several methods other than using a tripod exist, for example to use spike mounts, where a rod sits directly on the center of the benchmark. It is also possible to use threaded benchmarks or concrete pillars, where you screw an adapter or rod directly to the benchmark. Different types of steel structures are also used. Some of these setups, like the tripod and spike mount, are for episodic measurements of the benchmark, where measurements are made every year or every few years. The more permanent installations are for continuous measurements, where the position data are recorded continuously over years to decades. The continuous recordings require more infrastructure, such as solar panels, wind generators, and communications. What comes out from these GNSS measurements are time series of changes in position with time, such as shown in this figure. This GNSS time series, which is one of my favorite, is from a continuously recording station located at the southern slopes of the Eyjafjallajökull volcano. The motion of the station is recorded in three directions: east, north, and up. Note the scale on the axis. For the east component, for example, the total motion spans about 10 centimeters. The time scale on the x-axis is from the year 2000 to 2019. Behind each dot on the graph, there are 24 hours of data, measurements of code and carrier wave on both the L1 and L2 frequencies that were recorded every 15 seconds and then processed using specialized software to form one position per day. Before studying our volcano, we need to consider other processes that move the station. For example, melting of Iceland's glaciers causes an uplift of this station by about 5 millimeters per year. In the center of Iceland, this glacio-isostatic adjustment, as it is called, may be several centimeters per year. Looking at the east component, we can see that there are basically two modes of movement: a linear motion, interrupted by sudden motions, that occur around the time of the 2010 eruption of Eyjafjallajökull. The linear part of the motion is the station velocity. That is easily calculated from the slope of a line that best fits those parts of the data, shown by the blue dashed lines. We need to consider carefully what the station motion refers to. The surface of Earth is composed of several rigid plates that are moving in different directions by a few centimeters every year. Some plates are moving apart, while others are colliding or shearing past each other. There is basically no fixed place on Earth. All motion is referred to something else, for example, a particular tectonic plate. The time series presented here are in a special reference frame called the International Terrestrial Reference Frame, or the ITRF, which is sort of an average of the motion of all plates on Earth. Consider Iceland, where the North American and Eurasian plates are moving apart by about 1.9 centimeters per year. If the volcano being studied is on the Eurasian plate, then we want to use the Eurasian plate as the reference to eliminate plate motion from our time series. We are lucky with Eyjafjallajökull that it is located on Eurasian plate, because most other volcanoes in Iceland are within what we call the plate boundary deformation zone, where motion is intermediate between the two plates. Here, the time series of the same GNSS station has been referenced to the Eurasian plate. A map shows that the station is located about 7 kilometers south of the summit of the ice-capped Eyjafjallajökull volcano. Let's concentrate here on only the north component of the time series. If Eyjafjallajökull is inflating, it will push the station to the south. If it is deflating, it will pull the station northwards. From the year 2000 to mid-2009, the GNSS station moved towards the volcano by about 15 millimeters because of a slight deflation inside the volcano. In mid-2009, there was a short-lived small inflation period where the new magma flowed into the volcano. In early 2010, the station moved south by about 6 centimeters as a dike formed inside it. This dike formation is followed by a rapid deflation in the main eruptive phase in 2010. Interestingly, the volcano continues to deform after the eruption. Between 2011 to 2015, the station moves to the south, most readily interpreted as inflation of Eyjafjallajökull. Since 2016, the volcano has been deflating, shown by northward movement of the station. Data like these are very useful to understand and to monitor in real time how volcanoes are deforming on the millimeter scale.